Okay, on the, I believe it was the first extra credit I gave, I'm not sure how they're numbered on Blackboard. We had the card flipping problem where we flip a card, or guess a color, flip the card, and if we get it right, we get a point. If we don't get any points. And the question is, what's your expected value for number of points if you go through the entire deck? If you did not keep track of colors, your expected value would be 26. It would be a binomial, NP, P being zero point 0.5, N being 52. However, the problem was posed to say that you do use that information. In other words, if I flip my first one red, I'm probably going to guess black on the second one because there's 26 blacks left in the deck and 25 reds. So it becomes quite a complicated problem because at any point in the deck, say you flip 27 cards, you may have flipped 26 reds, and from then on out, you know everything's black. Or you may have flipped one red, and you know everything is, if I said that right, red on the way out. Or more likely, there's some reds and some blacks, and it just gets fairly complicated. So the first way I approached this was, and by the way, when I gave all of these extra credit questions, I didn't have the answer myself. So these are ones that I did have to work through also. So I like to make sure I get the correct answer first, even if it means a little extra legwork. And after that, then I try to find a more eloquent solution. So that's what I did here. I created a little spreadsheet, and this is the number of dominant so far. In other words, if I've flipped 3 red and 1 black, I would have 3 dominant. Whatever has been flipped more times, I'm going to say is the dominant. And you're always going to guess the other one. So if you have 20 dominant, if red is your dominant color, you're going to guess black. If black's your dominant, you're going to guess red, and so on. On the left side, I had flip numbers. So you can see here we have 52 different rows, 1 for each flip. So on flip number 1, when there's 0 dominance, because nothing has been turned over, there's a 0.5 chance of guessing right. On flip number 2, there will be guaranteed to be 1 dominant, right? Because whatever color I flipped during the first flip is now a dominant color. And so on that second flip, I have a 0.51 chance of being right. Why do I have, and that's not exact, that's a rounded number. Why do I have that number? Well, what's my chance? My chance of being right is 26 over 51, because if I'm guessing the color that has been less flipped over, in other words, if I'm guessing the one that's not dominant, then I'm slightly higher than 50% chance. In fact, all of my numbers should be higher, equal to or higher than 50% chance of being right, assuming I'm guessing the color that has been flipped least. Okay, when I get to the third, I'm also saying that I only have 1 dominant. How am I so sure? Well, if I, oh, sorry, I'm not sure. I could either have 1 or 2. So notice that on the third flip, I could have had 1 dominant. In other words, if I flipped 1 red and 1 black so far, or I could have 2 dominants if both of my first 2 flips were red or both were black. That's a better situation for me because it means I'm even more likely to get the third one right if I guess the non-dominant color. If 2 reds have been flipped and I guess black, I'm 52% likely to get that. So we go on through this. Notice that it does widen for a bit, and then towards the end it comes back a little bit. So this is the number of dominants, number of flip. Each number in here is the probability of getting right, assuming I'm in that position. Now notice most of these are 0 because I could never get to that position. For example, here, on my first flip, there's no way I can have 18 dominants. Similarly, down here, on my 15th flip, there's no way that I could have 1 dominant. Why is that? Couldn't I just have 1 red and 14 black? I could, but that would be 14 dominants. So whichever has more. So at the very least, I'm going to have 7 dominants by this point, 7 reds and 7 blacks. Okay, but that just gives me the probability of guessing right, assuming I'm there. I also have to look at the probability of actually getting to any of those particular positions. So for each of these positions, this is the probability that I'd guess right if I'm in that position. Here's the probability of actually getting to that position. Again, number of dominants so far and flips. So just looking here, for example, what's the chance that I would be 1 dominant on my 3rd flip? 51% chance. 49% chance that I would have, on my 3rd flip, I would have 2 dominants so far, either words, 2 reds or 2 blacks. Notice that these add up to 1, so do these, so do these. On any given flip, the probability of number of dominants should be they are mutually exclusive, and so they'll add up to 0. These will not add up to 0 because that's these could be, they're not mutually exclusive cases. You could be in this case, and then later in this case, then later in this case, potentially. So once I get each of those, probability of guessing right, probability of actually getting to that situation, I need to multiply those probabilities. Luckily with Excel, this is pretty easily just a simple formula. You can go to other worksheets and select a cell, and then just fill out. And after I do that, I just am going to select all my cells. You can't see this now, but at the bottom there's a place that says sum, and it says 30.04. In other words, I'm calculating the expected value. It's slightly over 30 cards right is what I would expect to get. So 26 by chance, 4, a little over 4 by the strategy of using the information previous. Okay, so this was a correct but long-winded solution. Ignore this right here. That's for another problem I was working on, Sudoku problem. Right here is what I want you to focus on. Okay, so this is another way to solve the problem. This is much more eloquent, and it involves a little twist here. So if you try this a few times, you'll notice that you're going to get 26, your expected value. 26 is random because if you're always guessing the color that hasn't been flipped yet, you'll always have that number left that you know are correct. In other words, if 25 reds have yet to be flipped, you're guaranteed at least 25 more in your expected value. Now, where it's a bonus is when it's a breakpoint. In other words, where there's the same number of reds as blacks. So in those cases, you could add a 0.5 to your total expected value. In other words, whenever you're behind in a certain color, so 3 reds, 7 blacks, you're going to guess red. And over time, that's going to accumulate. That expected value is going to accumulate to be 26. But then every time you hit a breakpoint, you have a chance at going slightly above that because you're not in that, it's kind of taking the pressure off. Whenever you're behind in a certain color, you really need to guess that color, and that's just what you're expected to get anyway. The bonus times come when you're hitting at one of those, at those breakpoints. So the question then becomes, what's our expected number of times when we have the same number of both cards? So at 0, we have 0 reds, 0 blacks, and so there's a 100% chance of that happening. So at the beginning, we have a 50-50 chance. So actually, right at the beginning, we have a 26.5 expected value. We have the 26 that we're automatically going to get by guessing the one that's behind when we're in those situations, plus we have the 0.5 from the very beginning. The next time this could happen is after 2 flips, because you could have 1 red and 1 black. What's the chance of getting here? Well, it's 50.5 0.9% chance that you would get to that situation where there's one red, one black. And you might wonder, why isn't this 50%? We either have red, red, black, black, red, black, black, red. If we were sampling without replacement, with replacement, then that would be the case, and this would be 0.5. In fact, the whole problem would be quite a bit easier. It would certainly be different. It would be much easier because the expected value would be 26 cards, right? But that's not what we have. We aren't replacing, and so we use that information. So we're slightly higher than 50%. Next time we can't have an even breakpoint at 1 and 3 flips. After 4 flips, we could have 2 reds, 2 blacks. What's the probability of getting that? This is a combinatorial problem like we had in the first few chapters. So I guess let me show you my formula here just in case you're interested. Okay, so I hope you can see that here, what I'm doing. But that's a fairly straightforward question where what's the chance that out of 4 flips you had 2 red and 2 black, assuming that you had 26 reds to start off with and 26 blacks to start off with. Okay, let me go back to okay, so we continue to go down here at the end. What's the chance, so at 50 here at the end, what's the chance that we've had 25 reds and 25 blacks? Do notice that it is symmetrical, so the chance right here. And you might wonder here, what's the 52? Seems like it should be a 1 here, that we have 26 reds and 26 blacks. But the problem is we don't get to guess anymore at this point. So these are really giving us an expected value of how many cards we're going to get, how many additional cards at that point. Now, if we sum these up over here, you can't see it, but the sum is 8.08, a little above 8.08. So there's, on average, we're going to expect to be in about 8 of these situations for every time we go through the deck. We're going to get in about 8 situations where it's a 50-50 call, where we have the same number of reds and blacks flipped so far, and so we just have to kind of toss a coin or call something randomly. So out of those 8.08, we would expect to get 4.04 cards correct, right? Because 8.08 situations where we make a 50-50 guess, we're going to get half of those right on average, so that would be 4.04. So in addition to the 26 we're getting right by actually guessing the underdog, I guess you could say, the color that's been least used so far, in addition to those 26, we're going to get an extra 4, a little over 4, through using that information that comes from those breakpoints that we get, those bonus situations. So add that together, we get 30.04, a little over 30.04. So this is, I think, a much easier solution to certainly to calculate. It's a bit harder maybe conceptually to see, though. I do want to mention the one student who got this right, got it right through Monte Carlo method. In other words, he did a computer simulation, just did a quick computer program where it would actually go through, pretty much doing what you would do if you went through the deck, guessing, recorded the number that you got right, then shuffled the deck, went through again, recorded the number you got right, assuming you're always guessing the one that has been least used so far. That's your strategy. And then you just average, do that 1 million times. I forget, I think the student that did this ran about 1 million trials, and then take the average of all those, and that should be a pretty good estimate. And indeed it was. He was within, I think, 1,000th of the correct answer, the correct theoretical answer, which is what we calculated here. Okay.